Agora sim. Bom, boa tarde a todos, né? Nós vamos iniciar, então, aí no SIBGRAPI 2020, a Technical Session 9, sessão Teca 9, Neural Networks and Classifiers. Boa tarde a todos que estão presentes nesse momento e bem-vindo a todos aqueles que vão assistir essa sessão eventualmente em algum outro momento, em algum outro local, né? Então, essa sessão vai falar um pouco aí, né, de Neural Networks and Classifiers. Serão 4 artigos que vão ser apresentados. Primeiro, então, eu gostaria de me apresentar. Meu nome é Flávio de Oliveira Silva, sou professor na Universidade Federal de Uberlândia, no programa de pós-graduação em Ciência da Computação, e eu vou apresentar aqui e acompanhar os nossos autores nessa sessão. Nós teremos 4 artigos que vão ser apresentados na sessão. O primeiro deles é Packet Vision, a Convolutional Neural Network Approach for Networking Traffic Classification. O speaker, né, quem vai apresentar é o Rodrigo Moreira. Então, a palavra está com você, Rodrigo, ou melhor, já está, né? O vídeo já vai começar a passar por aí e vamos aguardar aí após a apresentação.
The human brain is dedicated to see and vision. 80% of our memories are determined by what we see, and also about half of the human brain is dedicated to see and vision. Therefore, just as there are countless advances in computational intelligence, leveraged especially by machine learning techniques, it is necessary to pave the way for how computers see things. To this end, I, Rodrigo Moreira, from Federal University of Uberlândia, invite you to come with us to see how we imagine the ways that computers see network packets. Like quiz, Larissa Rodrigues, Pedro Froze Rosa, Rui Aguiar, and Flávio de Oliveira Silva had also involved in this work. Network traffic classification can improve the management and their service to offer, taking into account the kind of application. The future network architectures, mainly mobile networks, foresee intelligent mechanisms in their architectural frameworks to deliver application-aware network requirements, and the potential of convolutional neural networks, widely exploited in several contexts, can be used in network traffic classification. Thus, it is necessary to develop methods based on content of the packets, which can transform them into a suitable input for CNN technologies. Hence, we implemented and evaluated the packet vision, a method capable of building images from packets raw data, considering both header and payload. Our approach surpasses those found in the state-of-the-art, considering classification performance and the fully packaged structure characteristic, delivering security and privacy by transforming the package raw data into image. Besides, we built a dataset with 4 traffic classes and evaluated 3 CNN architectures, considering performance and the exploitation of the training from scratch, fine-tuning, and hyperparameter optimization.
Heitor, você pode nos ajudar? Então, mas parece que o vídeo voltou. Ok. Bom, pessoal, então, eu gostaria que vocês pudessem aí, né, ficar à vontade para enviar as perguntas, né? As perguntas aí para... Esse vídeo ficou meio... Haviam 2 vídeos? Oh, sure. I can talk in English, no problem. Sorry, guys. Well, I think we're starting now the question and answer. So this is a short video about the work, and I think that maybe a lot of questions can arise. So the idea was that you could see the video before, and then now we can discuss and ask some questions to Rodrigo that is here. So feel free to put your questions, and Rodrigo is here, and he'll be happy to answer them. So please feel free to put your questions. I don't see any question right now from the Wolva platform. Heitor, can you tell me if there is some questions from the YouTube streaming? Well, I don't see any questions until now to Rodrigo. Maybe I can do a question for you, Rodrigo. Can you explain, how the CNNs helped on the approach you used for the traffic classification? Did you try a different network, or that was your first choice?
Okay, can you hear me?
Sure, yeah, go ahead.
Thank you for raising this question. For the beginning of our work, we tried to understand how CNNs can help us in order to classify network traffic. So we choose the 3 kinds of network, convolutional neural network, and the challenge in which we face it relies on the packets always are in the same way. I mean, every packet have the 2 categories of information. The first one relies on the header, which implies the identification of the packets, and the second one relies on the payload. The previous methods we seen at the state of the art, we noted that all approaches consider only payload. So in this work, we consider both the payload and header. And by using CNNs, we achieve highest or a bigger accuracy than other methods, especially those found in the state of the art. And for future work, we plan to try another kind of CNNs, and especially to put other classes of the packets. As you can see in the Wolva platform, we choose 4 network classes. So we plan to improve this for more classes.
Okay, thanks, Rodrigo.
Okay.
Well, do we have another question? Well, if not, then I would like to invite The second author, is he present here? The author, one of the authors. So the next work is a comparison of graph-based semi-supervised learning for data augmentation. The speaker should be Lilian Berton from the Universidade Federal de São Paulo. So I'm not sure if Lilian is here with us. So let's see the video.
Welcome to SIBGRAPI 2020. I am Lilian Berton. I will present this work developed by my undergraduate student William de Oliveira in collaboration with Otávio Penati. This work is entitled A Comparison of Graph-Based Semi-Supervised Learning for Data Augmentation. Data augmentation techniques have been employed to obtain more labeled data in image classification. Data augmentation is the process of generating samples by transforming training data to improve the accuracy and robustness of classifiers. Previous works have demonstrated the effectiveness of data augmentation through simple techniques such as cropping, rotate, and flipping input image. The generative adversarial networks was first proposed by Ian Goodfellow. It's a framework for generating modeling through adversarial training. It creates artificial instances from a dataset such that they retain similar characteristics to the original set. Constructing data augmentation schemes, which result in simple, fast algorithms and improve the classification results, is a non-trivial task, since successful strategies vary with the nature of data present in different applications. We aim to perform a comparison among graph-based semi-supervised learning algorithms to augment the labeled dataset, and compare the results with image transportation and gains. Graph-based semi-supervised learning uses two different sets for training: the set of labeled data and the set of unlabeled data, where the labeled data is much smaller than the unlabeled. Given both sets as input, first we construct a graph where each example corresponds to a vertex. Finally, a label propagation algorithm is run on the graph to spread the no labels to the unlabeled vertex. This way, we can increase the label set with the labels predicted by the algorithm. So, giving a small label set and unlabeled set as input, the output is an augmented training set. We employed four graph-based semi-supervised algorithms: the label propagation, the local and global consistency, the Gaussian fields and harmonic function, and the omni-probe. Our methodology is divided in four phases. In phase 1, we randomly divide the dataset into train and test sets using holdout. In phase 2, we divide the training set into k-sets containing only 10% of the original data. In phase 3, we apply different data augmentation techniques into the k-folds until the set reaches the original training size. In phase 4, we apply convolutional neural network for feature extraction into k-training sets in the original test set. Then we perform SVM classification to compare the results. Regarding the data augmentation techniques, we consider image transformation, flip, field, zoom, translation, rotation, cut, the hypergun, and the four graph-based semi-supervised learning mentioned before. Regarding the convolutional neural networks, we consider four models: the ResNet 50, VGG16, VGG19, and exception. We employ five datasets. This table presents the classification results. In conclusion, all data augmentation approaches are effective to improve image classification. Graph-based semi-supervised learning presents high accuracy values and less variation in performance across the different datasets considered, showing good robustness to the different image properties. We thank you Federal University of São Paulo, the National Council for Scientific and Technological Development, and São Paulo Research Foundation to finance this study. Well, thank you everybody for your attention.
Okay, so thanks for the video. Well, I'm not sure if the presenter of one of the authors are here with us in this moment. Um, uh, Heitor that's here is here helping us. Heitor, can you confirm? Can you confirm that one of the authors, William Oliveira, Otávio Penati, or Lilian Berton? Um, okay. Well, I think so. Um, let's pass to the next work. Maybe we can get other questions to Ova. So at this moment, you can put the questions at Wova platform as well, and the authors then they will respond them later. So the next work that we have here will be presented by Wendel Magalhães from Universidade Federal de Campina Grande. It's named Evaluating the Emergence of Winning Tickets by Structured Pruning of Convolutional Networks. So please, let's see that presentation.
Hi, I'm Wendel Magalhães, master's student at UFCG, and this is our paper, Evaluating the Emergence of Winning Tickets by Structured Pruning of Convolutional Networks. Deep neural networks, or DNNs, have grown in size and complexity, become overparameterized, and with high computational costs. Neural network pruning tries to solve this drawback by removing redundant components or connections from these DNNs. And a wide range of pruning techniques follow three core steps: train, pruning, and then retrain. In most of the existing techniques, the standard procedure for retraining is fine-tuning, in which the pruned network is trained by a fraction of the unpruned network training epochs. However, recent works found that retraining unpruned DNA from scratch can achieve the same or even greater accuracy than unpruned or fine-tuned DNAs. Some of these retraining approaches are related to the lottery ticket hypothesis, which states that it's possible to find pruned networks, which are called winning tickets, from an overparameterized neural network and train them from scratch so that the pruned networks achieve similar or even greater accuracy than the unpruned network. An important step for implementing this hypothesis is to reset the weights to the initial random values. But recent works have proposed alternatives to this step that are 1. Resetting the weights to the value they had in an early epoch of the unpruned network training, which is called weight rewind. Or 2. Keeping the final training weights and resetting only the learning weight schedule, which is called learning weight rewind. However, we observed that most claims and conclusions of these works are based on experiments with unstructured pruning or structured pruning on hand-picked architectures, which means that the number of convolutional features in each layer of the resulting pruned architectures are predefined. In this context, this paper contributes with empirical evidence that supports obtaining winning tickets when performing structured pruning of DNAs. We evaluate and discuss the emergence of winning tickets using weight rewinding and learning weight rewinding on iterative structured pruned networks, with architectures discovered automatically during the pruning process, and compare these results with the same networks training with randomly initialized weights. In addition to that, we also investigate these retraining approaches for locally and globally pruned networks. We evaluate the emergence of winning tickets on the PGG16 network trained on the Cipher10 dataset. For that, we use the L1 node of the convolutional filters as the pruning heuristic and perform 10 pruning iterations, applying a 20% pruning rate at each iteration, as done in prior work. The following plots show the median, maximum, and minimum test accuracy from 5 different training runs, and for every plot, the x-axis is the percentage of remaining parameters, and the y-axis is the test accuracy of the network. So, in these plots, upper is better. We also show the accuracy of the unpruned networks as dashed lines, and the winning tickets are marked with a diamond shape when the accuracy of the pruned network is equal or greater than the unpruned. As you can see in this figure, the pruned networks obtained by weight rewinding overall present lower accuracy than the unpruned network and those retrained with random initialized weight for both pruning localities. No winning tickets emerged from local pruning, and from global pruning, few winning tickets emerged. However, random initialization was able to find more winning tickets than weight rewind. These results suggest that weight rewinding is not efficient for finding winning tickets in the context of structured pruning, and is no better than retraining the pruned networks with random weights. Unlike weight rewinding, for learning weight rewinding, we can notice a higher accuracy of winning tickets, and these winning tickets emerged even in later iterations of pruning, which means that the networks were pruned more aggressively. For example, we were able to find a winning ticket with approximately 12.1% of parameters remaining. Moreover, the pruned networks obtained through learning weight rewinding have higher accuracy when compared to those retrained with random weights. This is an indication that the learning weight rewinding retraining technique has a significant impact on the final accuracy of the structured pruned networks. However, winning tickets emerged only for global pruning. In conclusion, our findings suggest that winning tickets can emerge by applying structured pruning with architectures discovered automatically during the global pruning process, while prior work were limited to unstructured pruning and structured pruning with hand-chosen architectures. Overall results indicate that for both rewind techniques, the local pruning fails for finding winning tickets. Moreover, learning weight rewind outperforms weight rewinding and is able to find winning tickets even at aggressive pruning levels. Thanks so much for your time, and we are happy to take any questions.
Okay, thank you, Wendell. Thank you, Wendell, for being here with us. Um, well, is there any question to Wendell? Does someone here would like to put a question to Wendell at this moment? Um, well, I don't see at Wolva new questions at this moment. Um, well, Wendell, you talked about oops, just a moment here. Just a moment, I'm checking here the Wolva platform.
Okay, no problem.
Well, I don't see any question here, Heitor. Just to me, I think was just a single question A session, but I don't see any question here specific to Wendell or regarding this paper. See, yes, I saw it here now. What do you think about NVIDIA's auto-pruning tool? That's the question that we have here.
Thank you for the question. We in the development of this work tested a lot of pruning tools, but the level of configuration and setup that we needed was not attended by these tools. So much of the codes that we used on this paper were made by ourselves and only using the PyTorch framework. So I don't have much to say about NVIDIA's auto pruning tool.
Okay, thank you. Thank you. Well, I don't see no further question here at the platform. Well, Wendell, I would like to know, because you're talking about your future work here. Can you tell us a little bit more about that? What you plan to do?
Can you repeat the question, please?
I mean, regarding the future work you were you told about some future work that you plan to do next, right?
Okay.
So
Yes.
can you please tell us about what do you think you can improve the work and what was done until now?
So in the literature, a few works the, aim at pruning structurally. So we focus on structural pruning, and we aim to validate these results on more data sets and for more neural network architectures. So for future work, we aim to expand these results and even evaluate some other pruning heuristics, because in this paper we exclusively used L1R. So we aim in this direction.
Okay, thanks. Well, Wendell, there's another question here. Rodrigo Moreira asked you, Wendell, could you please clarify the difference between global and local pruning?
Okay. In global pruning, the convolutional filters are selected to be removed independent of the layer they are in. And for local pruning, the convolutional filters are pruned according to the layer they are in. So if we apply a 20% pruning rate, we will remove 20% of convolutional filters in each layer of the neural network. And in global pruning, these filters are removed regardless of the location.
Okay. Well, any other question here? I don't see at the WOVA session. Guys that are taking a look at YouTube, do you see any question from YouTube? Okay. Well, now, so in this case, I would like to thank you, Wendell, for the presentation, for being here with
Thank you
us.
very much.
And now let's see the next work in the session. The speaker is Marta Duarte from Federal University of Rio Grande, and she will present the paper Thermographic Non-Invasive Inspection Modeling of Fertilizer Pipelines Using Neural Networks. So please, let's see her presentation.
Hi everyone, I am Marta Duarte and I'm going to present you an overview of the paper Thermographic Non-Invasive Inspection Modeling of Fertilizer Pipelines using Neural Networks. So, industry pipeline faults like blockage can create big problems for engineers and major financial loss for the company. The blockage detection is necessary for a smooth functioning of an industry and for the safety of the environment. Our objective is to develop a non-invasive inspection model to identify the obstruction stage in industry ducts. So the idea is to use a thermal camera that acquires images associated with the temperature emitted by the external surface of the pipe, and this image will be processed by a neural network, and the output is going to be the deposit height. The hypothesis adopted is that the fertilizer has a lower thermal conductivity material than the steel of the pipe and the air that is inside of it. So here we have some examples obtained during the work. The image on the left was captured when the pipe was cleaned inside, and the image on the right was captured when the pipe had fertilizer sediments inside. Warm colors as yellow and red represent warmer temperatures, and cold colors as blue and green represents colder temperatures. So it is possible to observe that in the image on the right, the pipe temperature decreased with the addition of the fertilizer sediment, leading us to assume that the fertilizer acts as a heat barrier. Due to the inhospitable environment, we adopted a data set obtained in a controlled experiment. So for the scale data set, we use a scaled pipe, and some models of sediment deposit are manually elaborated in order to obtain the ground truth. these models are installed inside of the duct with the heat blower turned on, and then the external temperature of the pipe is captured with the thermal camera. The dimensions of the sediments models that were manually elaborated are obtained with a 3D scanner, and this way we obtain the ground truth. So the dataset input is the thermal image and the dataset label is the deposit profile. To do the association between the thermal image and the deposit profile, we consider a patch of the thermal image. We used two different ways to obtain the deposit obstruction. One considering only the pixel intensity of the patch, and the other one considers the pixel intensity and the height at which the patch is being extracted from the thermal image. For the fertilizer thickness image, the same patch is used, but we consider only the central pixel. In our work, we use patches of size 3 by 3 and 5 by 5 by 5 to compose our data set. So in our work, we concluded that the external behavior of the duct can be mapped in deposit profiles, as the neural network was able to learn the mapping of the thermal pixels in deposit profiles, obtaining some quite satisfactory results. And it is possible to detect the sedimentation that is occurring inside the duct from an external thermal image. Thank you for your attention. I am Marta Duarte, and here is my contact email.
Okay, Marta, thanks. Okay, Marta, thanks for your presentation.
You're welcome.
Well, it's a very, very interesting work, application work. Um, well, do you plan to extend this work, I mean, to other areas you're using in fertilizer ducts? Do you plan to use it to in different areas? Do you plan or see to apply the same ideas in different areas or different types, maybe with different, you know, uh, uses in the industry?
Yeah, actually, we are today we are working with only with the fertilizer industry, but we aim to extend our scenarios, not only on the fertilizer industry, but in other industries. Sorry.
Okay, yeah, sure, for sure. This kind of pipe problems is really a problem in industry in the whole.
Yeah.
Well, there's a question here that came from Nova platform. What was the error rate? The error rate, it was good for the problem. How do you see the error rate considering the problem you have? What's the error rate considered? This was good for this problem.
Yeah, we used some residual histograms to map the error and some color maps, and the results obtained were quite satisfactory. We used the 3D scanner to have the ground truth and to compare what the neural network predicted when what we already measured with the scanner, and the results were satisfactory.
Okay. Well, let's see if we have another question here. I don't see in the Wova platform. You guys, let me know if at YouTube, do you have other questions from YouTube? Well, it seems no more questions here. The guys that are in the session, there's another person. Whoops, now we have a question. Okay. It's maybe from YouTube. Can you put the question here for us? Well, the question from Rodrigo is, what supports this hypothesis of non-invasive inspection? So Rodrigo is asking, what is this non-invasive inspection? How do you, what supports this hypothesis?
I don't know if I understand understood the question, but we don't have contact with the pipe. Our idea is to extend our data set and have the work like we have had some answers for our work, so we could go to the industry and use our methodology and don't touch the pipelines. I don't know if I'm answering right your question.
Yeah, I think it's a kind of this. This was a question. I mean, this non-invasive inspection, right? But at least you need to get the image from the. You can get good image, right? Maybe the conditions you're grabbing this image can take into consideration or not. What do you think, considering this question? Just to go further on this, because you don't need to go inside the pipe. You don't need, but you can from a distance point, you can grab the image. You can catch the image, right? But what do you think in this? I mean, when you were far from the, in the field, because you test in the lab, right? With the pipe and things like that. Let's consider you are in the field. What do you think this could, you maybe interfere the images you grab? Like sun, lights, things like that.
Yeah. I think the weather can different a cloudy day, a colder day, sunny day can kind of interfere in the results obtained by the thermal camera, but we didn't study these conditions yet. But in the future, we are aiming to put the methodology in the real scenarios and see what we get.
Okay, like to stand the study, right, and see how it all fits in the real world. Yeah. Okay. Well, all right, Marta. Thanks for your questions. Well, we have a presentation. So we're finishing the session now. I don't see any other questions at this moment. There is a person, Lillian, that entered after the presentation. I'm not sure if the guys has some questions to Lillian regarding the work. We showed the video, but Lillian was not inside the session. Let me see here if we have some questions here, but I don't see any questions to what Lillian presented. Let's see here. Just a moment. Yeah, we don't see any questions here. So I would like to thank you all for being here and for sharing the presentations, for sharing this work with us. So I would like to thank you, the presenters, and hope to see you soon, some other place, some other place, and maybe in person when we could do this, if possible. So thank you all for being here. Thanks, everybody.